bag up.
Hey everyone, good afternoon. Hope everyone is doing well, hope you're enjoying the event. I am Matt Ellis, I'm a part of the product management team at Tibco Software. I focus on our open source tech stack, so more specifically Project FlowGo. Kind of everything open source related is what falls under my umbrella.
And hi, am I on? Hi everyone, I'm Abram Vandergeest. I am the machine learning project manager working with Matt on FlowGo. So basically it's my job to make sure machine learning gets integrated with Project FlowGo.
So Abram here will spend most of the time talking about all the cool stuff, and I'll just kind of bore you with some of the basic open source stuff and events. But I suspect open source is something you guys probably like, yeah? Awesome. So from an agenda perspective, we'll kind of break this up into several different categories. So we'll talk about events. And if you really think about event processing in general, especially in the context of traditional software, I mean, you've heard about event processing forever. So I want to kind of debunk some of the myths and talk about what we consider event processing today. We'll talk about how events kind of make sense and how events are translated into, or how events became the precursor to the big data movement, which then fed into IoT, which fed back into big data, and we'll kind of talk about some of this stuff, and then finally talk about some of the ML techniques that you can use, and then we'll jump into talking about specifically open source Project FlowGo, and we've got a demo lined up for you here today as well, so we'll walk through the demo, show you how it was built, and kick around a few boxes. So an event, at its core, is nothing more than something that happens, right? Typically speaking, it can be something of importance, but oftentimes a single event by itself is not usually something of importance, right? Usually it's multiple events that have occurred within a period of time that can be aggregated into a certain window that becomes something important, right? Like I said, an event is just an event. I could kick my box on the floor and that's just an event, but nobody really cares about that, right? But if I do it a million times, then clearly I've got a problem. So that's a derived event. So when you look at events in general and you kind of think about how you can process events, and you take a step back. So again, if we take a step back and we say an event, at its most simple form, is just something that happens. And processing an event, you can process events in multiple different ways, okay? So you can process millions of events at any given time. You can consume those events into a pipeline, stream those events, aggregate those events over a period of time, maybe produce some sort of derived event after the fact, okay? You can also do something along the lines of just integration. So a single event comes in, you integrate that event with something else. So maybe you write it to a database, or you publish a Kafka message outbound, or you do something like that, okay? You process a single event at any given time. But you can also process events in more what used to be the traditional complex event processing paradigm, right? So the concept is simple. Events come in, you store events in historical memory, you correlate events against past events with new incoming events, and then you produce you infer some sort of derived event from that, okay? So all three ways of processing the same simple concept, an event, okay? So in this session, we'll spend some time kind of diving deeper into that notion. We'll look at how you can process events, and we'll explore the open source framework Project FlowGo that kind of led to, or that enables you to consume, process, and build events in all of these different ways. So making sense of an event. So if you take a step back and think about it, so you've probably heard this phrase before. So data is king, okay? So what you can do with data produces some sort of outcome that's tangible or relevant for your business. Well, the fact is that, yeah, sure, data is important, but all data originated as a single event, right? So a single event came in, and over time, multiple events came in. You stored them into a data lake, a data warehouse, something like that, and you started saving these events until you had a huge chunk of data that you then needed to figure out what to do with. Right? So data volumes continue to grow. Oftentimes, you can't take the data itself is too large. You can't process the data and produce some sort of meaningful some sort of meaningful action with the data itself. So you leverage something like AWS for cloud scale to process this mass amounts of data, to train data, to produce machine learning models and produce insights from the events. But as I said, the data is growing, right? So more and more data sources are being produced every single day. And if you really take a step back and look at that, a lot of that has to do with the concept of IoT. So sensors are really literally everywhere. There's a sensor put in everything today, and everything is producing data. Everything is producing an event, okay? So that data warehouse continues to grow, and again, it continues to push, or the focus needs to shift onto cloud scale to truly process those events and actually perform something meaningful with those events. But that's all fine and good, so all this mumbo jumbo about data and data's king and events and all that crap. But what about architecture paradigms? So if you're a software developer, then architectural paradigms have also shifted, okay? So with the increase in data, people expect more, so your customers expect more from you because you're using their data to provide them some sort of insight. For example, churn prediction. If you've predicted a customer is going to churn, then you might give them an offer to try to keep them within your company. And oftentimes customers are okay with giving a little if they get something in return. So they're expecting more, your businesses expect more, they push back on IT, they push back on the developers, and the developers now need to start building software that can scale quicker, that can change quicker, right? So monolith, traditionally, the way we build software was a giant service with a ton of different capabilities embedded in that single service. Hard to change. If you did make a change, then oftentimes the service itself would, you'd break something else, right? So you'd make one change, you break something else, you might crash the service, upgrades were a nightmare, you had these all-night marathon software upgrades, things like that, so a total disaster, right? So then we moved into the realm of microservices, where we took that service, we broke it apart into a bunch of different smaller services, and each smaller service typically had 3, 4, 5 operations associated with it. Each service was typically bound to a business capability. So when the business came to you and said, hey, we need something changed, we need to do this, we need to do that, you were able to make a change to that single service. You didn't break the entire system. You updated that single service, but still you were potentially impacting, 4 or 5 other operations associated with that service. So then we move into the realm of serverless functions, or functions, right? So serverless and functions, they're not the same. I'm not going to get into that argument at the moment, but functions themselves, we move into the realm of functions. So you start building single discrete components that are tightly bound to capabilities. They perform one thing and one thing only, and that could be an update operation, a delete operation, transforming the data. Maybe you invoke a machine learning model or something like that. So you moved into that realm of software development. But you've also got another change that's happening, right? So you've heard it before, right? So AI is eating software, and that may be partially true, but the fact is that AI is absorbing software, okay? Or AI is augmenting software. So you don't write software the way you'd traditionally write software anymore. Traditionally, you'd write software in the sense that everything was a deterministic set of rules, okay? Ifs, else, procedural logic, things like that. That was your software. But today, the software needs to start shifting. It needs to become both predictive and prescriptive. In other words, what's going to happen and what can I do about it, okay? So with that shift in how you need to start approaching software, you need to start taking machine learning models. You need to be able to embed some of the ML techniques into your traditional applications, and then enable those applications to become predictive and descriptive. So that means machine learning is the answer for everything, yeah? Of course it is, right? My marketing department told me that if I put ML on my marketing material, that it'd sell. So that's why I created the slide. Joking aside. Anyway, so machine learning is not always the answer, guys. So sometimes you could actually solve a problem simply by performing some element of stream processing on the data, or some element of deterministic rule sets on the data itself, okay? So as the events come in, you can aggregate data over a period of time, and you could calculate the average over a period of time, or the median, or whatever derived value you're trying to calculate. And you clearly didn't need machine learning for that, okay? Some of it's just simple math, right? But oftentimes, you do need ML when you're looking at classifying large quantities of data. So you want to maybe do image classification. So maybe facial detection or recognition or something like that. Then you start looking towards ML techniques and algorithms and things along that nature as well. But there's a couple caveats. So you look at ML when you have a broad set of problems that need to be identified and detected, something that is far too broad of a set that you could manually do yourself, but that also means you need the data. So kind of back to that original point of data being king, you need the data, otherwise you can't train ML models. And I'm going to pass it over to Abram now, and he's going to talk a little bit more.
Okay. Hello. So I'm going to talk about a little bit about deep learning, AI, and ML. But first I'm going to discuss a bit of the differences between supervised and unsupervised learning in machine learning. So basically, as Matt said, we often have to integrate new capabilities within the microservices and functions that we are building. Supervised learning is one of the more common ways of doing this. This is where you are basically taking some inputs or features, which in this case can be represented by X, and we know in a certain number of cases that this should be the output, Y. So we're trying to build our model such that it determines what our function is. And this is the supervised learning approach in general. It tries to predict some observed condition. This requires a lot of data, but just not any kind of data. It requires labeled data. So you need to know what the output should be. So for my linear regression here on the lower left, basically, we see that there's a large number of points needed to basically determine what that line was with a fair amount of accuracy. So that in the future, we can now say, when we build it into our function, that if the input of X is given, say at 5, we know that the output should be something around 0.75 or something like that. That's basically the idea behind supervised learning. Now there are subsets of machine learning, of supervised learning that unfortunately apparently got lost in the transition to this slide deck, but they include semi-supervised learning, active learning, and reinforced learning. And all three of these are ways to use partial data to help you learn. So semi-supervised is using some incomplete set. So if you're trying to determine outliers, for example, you might know that 10% of your data is an outlier, and you can use that to train your model. Active learning is where the algorithm decides what specific cases will be most useful for it. This is often integrated with interactive learning. So when it determines a point should have a label, it'll kick that out to a human being who would then label it. Reinforced learning, which is hidden behind the plot, is basically where your model makes a prediction and then you either punish it or reward it based on what its result was, such that it continues learning. Now, all of this is supervised learning. You have example cases to make predictions from. Unsupervised learning is where you just have your input data and you don't know what possible outputs could be. So this is often used to explore your data, to understand the structure. Detect anomalies is often very common, but just generally to uncover new phenomenon. Now, one of the limitations of this is depending on what your input features are and how you decide your input data, this can greatly change what your outputs are. And so this leads to why you are doing unsupervised learning. So basically, unsupervised learning can either be the point itself. You want to know what your data looks like. So whether it's clustered, how many clusters could exist in your data set. Or you can be trying to determine what your classes should be such that you can put this into a supervised model or things like this. For example, my clustering data set here in the lower right, you can see that the data set really is clustered within 3 categories, such that after we run our unsupervised approach, we will know that there's 3 clusters, let's call them A, B, and C, such that we can then use this for our supervised approach. Now, both supervised and unsupervised learning can be applied to many, many things. Here I have 6 categories of applications. As you can imagine, there are many, many more. And within those categories, there are lots of smaller tasks that can be that machine learning can be applied to. All of these have and so on because these are just a quick sampling of what possibilities could exist. Now, classification and regression are probably the 2 more common types of machine learning applications, or at least they're the ones that you're probably most familiar with, where classification is, well, you're classifying things. You're trying to detect whether it's a fraudulent event or not, whether it's spam, or you're trying to bucket your data into any of a million different categories. This is one of the ways that recommendations engines work. While regressions are basically anytime you're fitting a graph or trying to predict the value of something, you're doing a regression. So these are the 2 most talked about and used types of applications. But you also run into clustering and pattern recognition, which is often an unsupervised approach, where you can discover classes and features. You can also do dimensionality reduction, which basically there are many, many cases where you have a lot of possible inputs for your data that slows down your supervised or machine learning approach. And so you want to find the most important features. This can either be for the supervised approach or just because you want to know what's causing your client to churn. And so that you can address that. All this can be done with dimensionality reduction. One of the more famous dimensionality reduction examples is actually with natural learning processing, where originally people would have a very sparse matrix where every word that they expect to see corresponds to a 1 or a 0 in a very long list. However, this can be on the order of 100,000 columns in your row and can be very difficult to handle. Word embeddings is basically a way to reduce this down such that every word is represented by a 300-dimensional vector that's a float. This is much more efficient than having 100,000 or a million column sparse array. And then, of course, we can also do outlier or anomaly detection, information filtering, or any of 100 other applications. So we sort of started this section with deep learning, machine learning, AI. What's that? Well, hopefully, after this slide, you'll have a more detailed understanding of at least my interpretation of this. So I want to add the caveat that if you get 10 data scientists together in a room with this slide, you'll probably get 20 different opinions on how this all works. But basically, machine learning is algorithms that you basically try to extract information out of data. While artificial intelligence is a computer system that seeks to emulate human thought or human intelligence and activities. So seeing, listening, understanding. Now I have them here as 2 separate bubbles that overlap. There was recently an article on Medium that actually had AI as the larger bubble with machine learning completely inside. I actually feel that this is not entirely accurate because there are forms of machine learning that is not artificial intelligence. I'll actually say linear regression that I showed earlier is an example of this. Human beings are horrible at drawing lines, but linear regressions are actually pretty good at it. While for artificial intelligence, there are forms of AI that are not based around data. Originally, a lot of AI was rules-based. Now, of course, the more recent forms of AI and the more sexy forms are more related to data, but that is not all cases of AI. So that's why I break them apart into 2 overlapping circles. Now, neural networks is a class of algorithms that are modeled off basically human neurons. They use linear algebra to basically try to replicate how the human brain works. Now, deep learning is a subset of neural networks, basically a hierarchical form. So here you want to think multiple layers, where the lower layers try to find their own representations within the data. So an example of this is in image recognition, where the machine learning algorithm gets just the pixels of the image. The first layer of the network will look at the pixels and try to form lines. The second layer will take the lines to try to form shapes. The third layer will try to take the shapes and try to form faces. So on and so forth until your final layer tries to predict facial expressions or things like that. So you can actually see that deep learning is a subset of neural networks that is also a subset of both artificial intelligence and machine learning. But that AI and machine learning don't completely overlap themselves. So I think at this point, I'm handing it back off to Matt.
Thanks, Bram. So we figured we'd bounce around between each other just to try to keep you guys entertained and keep you from getting too bored. So I'm going to shift gears entirely and talk about Project FlowGo. So Project FlowGo is an open source ecosystem for event-driven apps. Okay. So when we set out to build Project FlowGo about two-ish years ago, we kind of set out with a couple key initiatives in mind. The first initiative is that it had to be lightweight. Okay, so it had to be efficient from a resource consumption perspective. You know, if you look at traditional Java apps and things like that, enough of that crap, right? Where you've got a JRE that's 190 megabytes, you've got consuming at least several gigabytes of RAM on your application and things like that. So 10 to 50x lighter from a footprint perspective was one of our goals. Another thing that we set out to do was make this an open source project from the beginning. So rather than some projects that start as kind of closed source and then eventually become open source, we wanted this to be an open source project from the very beginning, where you'll see a lot of the proposals or the early proposals and some of the stuff that kind of drove the project to be what it is today was done through the community, and that was incredibly important to us. Number three, we wanted, I can't count. Number three, we wanted to build a common core or a common application kernel that would enable us to process events in varying different capacities. So kind of what I talked about a little bit earlier. Our initial implementation was a process-based a flow engine that essentially processed single events at any given time. And then we've expanded that going forward as well. So one of the elements was that we also needed to deploy anywhere. So deploy on devices, but also deploy on serverless functions as well. So FlowGo runs natively on AWS Lambda, so you can build an application, package it up, deploy it on Lambda, take that exact same application, package it up, and push it on an IoT device, or bundle it in a Docker image and deploy it on K8s or something like that. And then finally, machine learning. Machine learning was a core pillar of the project. And it was a core pillar of the project in the sense that we wanted to build a set of tools that developers would consume to enable them to consume ML models and techniques, okay? So it wasn't that we wanted to build yet another tool for the data scientist, but in fact, we wanted to build a tool for software developers so that software developers could then consume the various ML models that people like Abram might build in his spare time. So when you look at this, so it's an ecosystem, as I said, right? So when you look at this picture, you've got integration flows that we kind of talked about a little bit earlier. You've also got stream processing. You've got contextual rule processing, and you've got a micro gateway implementation. So all of these various event processing capabilities implemented within the FlowGo ecosystem that leverage the same common application kernel, okay? And by leveraging the same common application kernel, that allows us to consume and take advantage of the over 500 contributions that exist in GitHub today. So all of the various contributions that other people have built and extended the project with can be used in any single one of those event processing capabilities as well. But just taking a step back, the common kernel also provides a powerful event-driven kind of programming paradigm. So from the ground up, it was built with this event-driven paradigm in mind. You've got this notion of both actions and triggers as well, okay? So a trigger is what produces the data element. So that could be a Kafka consumer, okay? So it's consuming messages off a Kafka topic, and then passing that over to an action, and an action is implementing or processes that single event. And an action can be a stream processing action, so you can consume thousands or millions or billions of events off of a Kafka topic, aggregate those over a period of time and do something with them, or you can integrate every single individual event depending on how you want to process the event itself. So it's not Mario dressed up as a bird or anything like that. But in fact, this is our integration flows. So integration flows, as I said, was kind of the first implementation of an action type. Okay, and this is fundamentally a process engine. Okay, so it's a process engine that was designed specifically for application integration, but you can leverage it in a lot of different capacities. State. It can persist externalized state, but typically speaking, in the context of microservices or functions, most of the stuff is stateless. You can do things like control flow implementation and things like that. So you kind of control the logic and implement procedural logic within your application. But one of the other things that was important to us was that we wanted to reimagine the developer experience. So a couple years ago, you take a look back at kind of the developer landscape, and especially if you looked at the Java world, you had things that ran on big, beefy IDEs. You needed a gig of RAM just to run the IDE itself. So we really wanted to reimagine that experience as well, and rather than having a thick client, we built a web-based development environment. That web-based development environment supports unique features like step-back debugging. So you could debug your application in the web browser, and you could step through the activity and introspect the inputs and outputs of each activity and things like that. So when you look at the process engine itself, the process engine, it does a couple things, or it's designed to do a couple things. So you build or it orchestrates the execution of activities, and an activity is nothing more than a unit of work. It's something to do, okay? So it's log a message, write something to a database, publish something to Kafka, read or write from a WebSocket server, write to a SQL database, whatever the case is. It's just a unit of work. It does something. So the process engine itself manages the execution of that. So you can implement things like conditional logic and branching. So you can deviate the execution flow in order as well. And fundamentally, it does manage state. There's an externalized state service that you could leverage that would allow you to do things like if an engine were to shut down, it could start up and rehydrate from a certain point going forward and things like that. The user interface looks something like this. So one of the unique elements of this particular interface is essentially everything in that gray area is basically a function. So if you go back to that initial concept of moving towards function development rather than just microservices, everything in that gray area is a function, and you abstract the function call by defining a function input and output declaration. So just like a function in any procedural programming language has both an input and an output, so does a FlowGo action. Okay, the action has both an input and output, and then you can abstract away the triggers itself. So I can have a Kafka trigger today. I can put in an MQTT trigger tomorrow. I can put in, I don't know, a physical general purpose interface trigger or something like that and consume off of an IoT device in a week from now without changing any application logic. So FlowGoStreams was something that we launched actually in September of this year. And FlowGoStreams, the core purpose of this project initially set out as okay, so if we're processing a set of IoT data or data off of sensors, we need to, oftentimes the data itself is far too granular, so we need to aggregate the data and kind of up-level it a couple levels. So we initially set out to build FlowGoStreams, and FlowGoStreams provides a couple key capabilities for that particular mission, which is both data aggregation, provides grouping and joining against multiple data streams, and then also allows you to filter out any noise or any unwanted data elements or events. So when you think about the grouping and joining, this is incredibly powerful. So if you have the concept of Kafka MQTT and that GPIO interface that I talked about, producing events, you can group off of an element within the payload of every single one of those events, group off of that element, and then pass it into that single stream pipeline so that you can aggregate across event sources as well. So incredibly powerful. The ability to both group and join off of those events. But also data aggregation. So data aggregation is clearly something that's pretty important from a stream processing perspective. So we support a number of different elements. So we support both tumbling and sliding windows. You could do time tumbling or event-based tumbling windows and sliding windows. And then from a function perspective, at the end of that aggregation window, you can do an average, a sum, a min-max, a count, or you can accumulate it. So in other words, accumulate it into an array and then process that array later down the execution pipeline. And then lastly, that brings us to FlowGo Rules. So FlowGo Rules is our contextual decisioning engine that's built on top of the same application kernel, and that's part of the ecosystem, okay? So one of the use cases with FlowGo Rules is that classic event processing use case, right? So you consume events. Maybe there's nothing to do with the events that come in, so you persist those events into memory, which we call a fact. So you persist them as a known fact, and then as new events come in, you can group those new events and join those new events off of the known facts that already sit in memory. And then you can take action based on that. So the classic example is fraud, right? So if I use my credit card here in Las Vegas today, that's probably fine. Depends where, but it's probably fine. And if I use my credit card tomorrow or in an hour from now in San Francisco, that doesn't sound right. So that's the classic example of contextual deterministic processing. So shifting gears just a little bit. So I said machine learning was a core pillar or a core construct of the framework entirely. So we support natively TensorFlow within our application, the applications that you build within FlowGo. So any application that you build, whether it's a stream processing app, an integration app, a rules app, whatever, you can leverage the TensorFlow inferencing capabilities. And again, that's all open source. And the way we built the TensorFlow inferencing capabilities was kind of in a modular form. So we initially set out, so we built a generic model and framework implementation or representation, and then we abstracted away the TensorFlow details from FlowGo itself, and then we built the native FlowGo implementation on top of those interfaces. So that does allow you to leverage maybe MXNet in the future or something like that. But to be quite honest with you, I mean, TensorFlow has kind of become the de facto standard when it comes to deep learning frameworks, and I'm quite comfortable with our TensorFlow implementation at the moment, but that doesn't mean someone in the community couldn't build MXNet or something like that later as well. So how many people use TensorFlow today? It's a fair bit. Awesome, okay. So then in that case, you'd be familiar with the concept, and TensorFlow has this concept of saved model metadata. So when you build a model and you export the model, the metadata is essentially a definition of what that model does, right? So what is the input to the model? So what is the feature set that it expects? And what's the output of the model as well, okay? So the FlowGo implementation abstracts all this and then leverages this for both validation as well as parsing data back and forth between the raw tensors and the FlowGo object types themselves. So I'm not going to get into a ton of data on this. It's a little bit boring and a ton of text. So I'll let him finish his picture and move on. Okay. So everyone here that's used TensorFlow, you know that you can operate TensorFlow at multiple different levels. So you can operate TensorFlow at the raw graph level. And to be quite honest, that's a bit of an annoyance, right? It requires a lot of boilerplate Python code and just lots and lots of code to build up your complex graph. So about a year and a half ago, something like that, a year and a half ago, TensorFlow launched the estimator package. And the estimator has a bunch of different benefits that Abram will go into detail with in just a few minutes. But what really from our initial perspective was that it abstracts away a lot of that. So you can leverage the tensor or the estimator package. You get these pre-made estimators, so it's things like DNN classifiers, regressors, linear classifiers, things like that, all come out of the box, and you can build your own estimator as well, and then leverage that within the same framework, and then the exported output of the TensorFlow models all fall into that save model format, which makes it easy to parse and manipulate. So I've kind of alluded to this a little bit, but if you talk in the context of IoT, why do you want to place ML at the IoT edge, right? So I would also argue that in many cases, you actually hear the phrase IoT being replaced with edge compute. And I'd argue that that's probably happening because these devices are becoming more and more smart, right? They're becoming just powerful enough that they can apply some elements of smarts without needing to rely solely on the cloud. I mean, if you look at some of the stuff that Greengrass provides, then you could see that being able to run app logic at the edge, leveraging a framework like Greengrass, pushing out models, leveraging an application framework like FlowGo to build your applications that then run in Greengrass is pretty powerful. So back to the initial question is, why do you do ML at the edge? Well, data volumes, right? So it's kind of like we talked about at the very beginning of this presentation. Data volumes are continuing to grow, and oftentimes being able to stream that back to the cloud and then process all at the cloud, I mean, you'd be streaming back massive amounts of data. So theoretically, moving ML logic and inferencing to the edge, you could theoretically reduce your ingress costs alone by a considerable amount. And then also the predictions are closer to the source of data as well. So being able to predict and take action at the source also reduces any sort of prediction latency that might occur if you were dependent solely on the cloud for inferencing. So we do have a demo. I'm going to pass it over to Abram in just a second. So the demo itself is interesting in the sense that what we did was we built we took a Raspberry Pi. In fact, I've got the Raspberry Pi right here. So we took the Raspberry Pi, stuffed it into a box, and then we said, what if we could attach an accelerometer to the Raspberry Pi? And what if the accelerometer could pass its readings into a FlowGo application and then into a TensorFlow model? Could we predict what's happening to the box fast enough so that it appears to be occurring in real time? And it turns out the answer is yes. So I'll show you this in just a few minutes. For now, I'm going to pass it over to Abram to talk, to actually talk the details.
Okay, so I'm going to talk a little bit of building the machine learning model that went into our box. And basically what this model needs to be able to do is to predict or to label when the box is standing still, moving, or when it has been dropped. And here you see 3 examples, one for each of those cases. Oh wait, I can push it here. Now it's important to label your data correctly. So as you can see, for the moving and stationary, it's pretty easy for that data set that we have. The whole thing is moving, the whole thing is stationary. But for the drop, it's more complicated. You can actually see by eye, as a human being, you can identify where the drop occurs. It's pretty obvious, right? But then you need to know what's happening before that. Is that moving? Is it stationary afterwards? And this greatly complicates some of our model building. So basically what I've done for this case is I actually went and looked at our several drop examples and by hand drew the barrier lines. Now you'll see when I train the model that this ends up causing to have a little bit of noise on either boundary. So we'll see a little bit of bouncing around of what the label is. But for the most part, that only happens at these boundaries because it's ambiguous. And even a human being has a hard time drawing where these lines happen exactly. And so here I quickly, I apologize for the colors. I'm just trying to make sure you guys are awake at this time of the day. But basically, I end up creating a test train split of our data. I'll talk a little bit about more of that in a minute. Then I put this into a TensorFlow estimator and end up putting that into our model, and we get about 90% accuracy for our labels. However, that's when I put in, oops, sorry, wrong direction. That's when I actually label the left-hand part of the drop as moving and the right-hand part as stationary. When I leave those ambiguous regions off, I actually pump up my accuracy to about 90%. Now, part of that is because I am leaving out the messy portions, but also part of that is I'm improving my estimation such that I actually know discretely what each region is. Now, I want to point out the estimator portion of this slide, because this is where it actually becomes very useful to use with SageMaker. Because the estimator in TensorFlow actually abstracts out all the complications of mapping it to a GPU versus CPU and doing a lot of the more complicated things that you can do when you build the graph yourself. The estimator does this all for you. So when you go to SageMaker, which I can go ahead and do here. So here I have my instances set up, and I will go, now I've already created the tabs, but I will go to my notebook, my Jupyter server, where I've already set up, I think, an AIM204 something instance to run my Jupyter notebook. However, I can choose something much larger than this if my model ends up being huge, and the estimator basically covers any complications and such that between the estimator and SageMaker, I don't have to worry about GPUs versus CPUs. I just select the larger model and then allow the TensorFlow estimators, the larger compute unit, and I can allow estimator from TensorFlow to handle all the complications for me. And so from there, I end up, I have a notebook here for running and training my data. And as you can see, I basically, I will actually go ahead and create a terminal, which is one of the nice things about SageMaker. And I can go into my, oops, I'm not selected on the, there. I can go into the SageMaker directory, and you can see this is just like my Jupyter server. And I have all my data I have all my data in all my data in this directory, which I have unzipped using this terminal previously. From there, I actually define my boundaries for my drop. So each of these, this dictionary that I'm creating is basically just drawing the lines by hand so that I don't have to worry about that later. And then I basically process the file where I take the XYZ accelerometer readings, and I create the magnitude. So for every time period, I have 3 accelerometer readings for each direction, and then I have the magnitude. And from that, I'm plotting the magnitude for each of my files. So this is one that's moving, this is one of my drop examples, so on and so forth. And the vertical lines are where I define the drop regions to have ended. And I do this a couple times so that you can see the graphs nice and pretty. And as you can see, unlike my earlier example, the sitting is actually scaled to everything else, so it actually is stationary opposed to a lot of the jiggle you saw earlier. From there, I actually need to do the same aggregation that in FlowGo we do with the streaming engine. So basically, we take the previous 10 time steps for any given time step and add that to our rows. So for every time step, we have the current XYZ acceleration, the magnitude of the acceleration, and then I have the next one over, time -1, time -2, so on and so forth. So I ended up having 44 features for every time step. And the nice thing about this is I've now basically extracted out time, so it's not each row is not dependent on the rows around it because I've already taken care of that. So I can now just shuffle and take a test train split from this data and sorry, here's where I actually apply my function, and then I label the data because that's useful. Oh, and I am leaving out one more important, let's see. Here I take my test train split, but before that I actually choose one of my drop files such that it is not included in the training set, such that I can, or the evaluation set, so I can show you the results of some data that it has never seen before, and we can see how it works. And I realized that I actually forgot to run all here. So it's going to be running while I talk. And so that's what I'm doing here, is my extracting out one file. And then I do a little bit of overhead where I define which directory I want my estimator to save the training data, the training checkpoints from. And I also define the size of my model. So basically, the estimator I'm using is called a deep neural network, which is basically just a standard, fully connected, multi-layer neural network that is one of the estimators provided by TensorFlow. In this case, I was trying to use an example that used one of their pre-built estimators. However, if you wish, you can also build your own model, export this into an estimator, and so you can still get the benefits of SageMaker with the parallelization across all the units with your hand-built models. And in my case, the DNN starts off with the first layer with 100 nodes wide, and then the second layer is 40 nodes wide. And then since I'm making a prediction of 3 objects moving, standing still, and dropped, I have 3 nodes for my last case. It is now training. I then end up saving my model, which is sort of interesting. Let's see, where am I here? So in my models directory, I end up getting a lot of the checkpoint information, but I also end up getting this timestamp directory, which I will also point out. And here I get one file and one directory. The file, the saved model.pbtxt, is the format you need to put into FlowGo. So basically, this has all the descriptions of the neural network and all that metadata that Matt was talking about earlier. Variables then has all the values of all the variables that are included in that neural network. So here is where all you basically, once I'm in that directory, I just zip -r. And then I put in the ones I want. And of course, the computer froze on me for a sec. I then zip this with the variables. And this provides a zip file that you just put into your FlowGo app. So basically, when you build your FlowGo app, you just put this in the same directory as the app. And that's all you need to do to transfer your model across. OK? And okay, because of the lag, I screwed that up, the zip up, but you get the idea. So once I have saved the model, and then I can zip it and move it to FlowGo, I evaluate it, and that accuracy is 1%. I must 100%. So I'm doing really good, or I made a mistake along the way, and which is what I'm probably figuring is the case. But so you can do the evaluation, but then. That's from my 20% test split. But if I go and look at my extra data set, I can see here that I have, in blue, is the accelerometer reading. And you can see the region that should be a drop is labeled as such. So having a value of 2 on the right for orange and green is drop. So for the labeled data, it starts off with a little bit of motion, and then it jumps to dropped. For the predicted data, it's showing that it's already acting pretty heavily, and so it's calling it a drop from the beginning. Then there's a little bit of noise around the transition from the drop to stationary, but that's actually pretty reasonable because, I have a hard time drawing what that line was. I probably spent half an hour trying to find where it was the most obvious, and it's actually quite difficult to do. So I think this ends up showing that the model ended up working pretty well. And so that is where my part of the demo ends, and I will hand it off to Matt, and hopefully he'll be able to demonstrate actually what the end result is.
Thanks, Brom. Yeah, let's go ahead and so essentially what happened was, while he was talking, he trained the model in SageMaker, and it finished before he was finished talking. So either he talks really long, or SageMaker actually trained the model pretty quickly.
Probably the first.
Okay, so I talked about this box, so sorry for the noise here. I'm going to just tape the box up so I don't lose my Raspberry Pi here. I'll tape it up, and we'll show you what you can do here. And again, sorry, we were budget constraints. We didn't have money for scissors, so. Okay, thank you, sir. All right, let me go ahead and start this up. So right now I've got a shell open up to the Pi that's in the box. So I don't have it running all the time, so I'll go ahead and just start it up. So we'll start up the demo. What's happening is it's streaming data over to a WebSocket server with the prediction. So as I'm walking, you can see the cartoon starts walking. If I stop, the cartoon will stop, right? But if I walk some more, the cartoon will walk some more. So what's happening is that the data is being streamed off of the accelerometer into FlowGo, and FlowGo is identifying what it is that's happening, right, using the TensorFlow model that Abram talked about. But there's another key bit. So if I set the box down, what the box also does is it uses the rules engine to correlate against historical events, so it knows that it's sitting. It's keeping the context of the event itself. And then after 15 seconds, it can identify that it hasn't moved when it should have, and the box will start screaming at you, okay? So even further, if I pick up the box and I show you another example, so you saw that Abram talked about the dropping, right? So what if I take the box and I throw it? Then the cartoon will also identify that it's fallen and thrown. And I probably shouldn't have thrown it so far. But it looks like it still works. There we go. So all of that coming off of the accelerometer being passed into FlowGo. Okay, so again, we'll drop the box. And then I'm going to switch over to the slide deck, which is the button here. Thank you. Okay, let's talk a little bit about that. So what's actually happening is there's an accelerometer attached to the Raspberry Pi. The accelerometer is producing 3,000 data points per second. Okay, so it's producing an XYZ value for essentially every millisecond. What's happening is that's being fed straight into a FlowGo streaming application. So we built a trigger that reads directly off of the ADXL345 accelerometer. We feed that into a stream pipeline. The stream pipeline in real time is aggregating the data over 50 millisecond windows, and then it's passing it over to another aggregate operation, which is lagging the data. So Abram and I were talking about this morning, and apparently I did it exact opposite of what he was expecting me to do, but it still works. So what I'm doing here is aggregating the data, but doing it in a tumbling window, and collecting 10 events. So basically every half second, the machine learning model ends up inferencing. So the TensorFlow DNN ends up being inferenced every half second. The result or the classification of that inference is passed over to the rules engine, okay? The FlowGo Rules engine that's running on device as well. That's collecting in that event. It's persisting the current state of the box, and then it's waiting for the state to change using various different timer triggers and things like that, waiting for the state to change. If it doesn't change within a certain predefined window, the rules engine kicks off a series of rules, executes those series of rules, and then passes over to a flow. So the flow application then just simply logs the data. So if you looked at my console, it's just got a huge set of log data entries, and then does a WebSocket message outbound to the cartoon that you just saw. And all of that is running on the FlowGo application. So the FlowGo application itself is 10 megabytes in size, okay? Or actually, sorry, just under 10 megabytes. So just under 10 megabytes in size, running on the Raspberry Pi, taking in 3,000 data readings per second. So clearly you want to get started with this right now. I'm sure you're going to run and do it immediately. So you can go to our GitHub page, so github.com, tipcosoftware/FlowGo. In the examples directory, we've got a couple examples of Python notebooks and things like that that you could pull and you could bring into SageMaker, or you can go to the SageMaker GitHub page and look at some of the examples there. And then SageMaker has a free tier as well, and you could leverage that also. So with that, any questions? Yes, sir. I think we might need a mic, though. Otherwise, no one else is going to hear you.
Or I can repeat it if he... Go ahead.
Yeah, what is the memory and the CPU of your Raspberry Pi?
What is the memory and CPU of the Raspberry Pi? The Raspberry Pi is a Pi 3B, but we've run it on a Pi 0 as well. The footprint, or the SD card it's a 32 gigabyte SD card, but the application itself is only 10 megabytes in size. Sorry, he had the question. Let's just get to him.
Can you say something compared to
Apache NiFi? Well, I mean, it's radically different. So FlowGo is built entirely in Go, so it's Golang based. So it produces statically compiled binaries. From an event processing perspective, there are clearly a lot more event processing capabilities that FlowGo can accomplish as well. So it's not just streaming. FlowGo can implement a lot of other capabilities, plus the native ML inferencing stuff. But happy to jump into a deeper discussion if you stop by the TIBCO booth later this afternoon in the exhibit hall as well. Yes, sir.
Just out of curiosity, is there a particular reason why you chose for your drop detection not to just simply do an edge boundary, a certain acceleration as a drop across the board? Is there some dynamics involved in that you're trying to exclude from transit or something like that?
So a couple of things. So we wanted to do more than. Oh, sorry. The question was, why use an accelerometer and rather than just bounding the edge?
Why do a machine learning model instead of just putting a boundary?
Just boundary detection. Yeah. So why an ML model rather than just boundary detection? The answer is rather simple. So we wanted to do more with the data than just detect the drop. We also want to detect the general movement and then potentially the lack of the data. So that's why we chose the ML model. Unless you have anything else to add.
So I did look at that. I mean, we were hoping to have a machine learning model to demonstrate, but I did look at the hard part's not the drop boundary. Or whether it's dropped or not, it's being able to tell the difference between moving and dropped, right? It's easy to determine when it's stationary, and actually the machine learning model is much better because of that having to worry about the moving step. So this is not that different than that. And so because of the history that helps with the moving, it actually works a lot better to have the machine learning model. Unfortunately, the threshold is a little bit more robust ultimately, but you do get a lot of value out of machine learning.
Any other questions? Yes, sir.
So if I have a conditional flow,
Uh-huh.
and one path takes me down something that needs a certain compute capacity, maybe a CPU, and another path takes me down where I need a GPU. Is FlowGo essentially dumb with respect to that, or does it completely rely on like device markers inside of TensorFlow, or outside of the infrastructure behind it? Does it have any cognizance of that capacity?
Yeah, so the question is, if I've got two conditional branches, one branch that might require or might perform best against a CPU and another that might perform best against a GPU, can FlowGo identify which hardware optimization technique should be used? And the answer is FlowGo is for the most part dumb in that sense, and it leverages TensorFlow. So you can have different inference activities added within your flow, and then you could have each inference activity specifically marked as CPU versus GPU. Though you do get into potential issues with the dynamic lib that's built as well, and how that's optimized. So if it wasn't built with the GPU markers, then you're not going to get GPU optimization as well. So it really falls onto TensorFlow. Yes, sir.
At any point in time, is this cloud, so say when I drop the box, maybe I want to push some log data to S3 or something.
Yep.
Is that something you can do with FlowGo, or is it all on that part?
Nope, absolutely. So the question is, at any point in time, if I take data and I want to, identify a key event and then send that data up to the cloud, so write something to an S3 bucket or whatever, right? And the answer is quite simple. So FlowGo has native activities that'll allow you to write directly to S3 or MQTT outbound and things like that. So in an ideal scenario, you'd probably you do the aggregation and the processing at the edge, dump out those 3,000, rather than sending 3,000 events per second to the cloud, you'd send one every minute or two, depending when it's dropped. So yes, you can do that.
And it's fairly easy to do. It's effectively just putting another box in this chain, and it's really simple to add that extra box.
22 seconds. All right, everyone. Thank you very much.